We're starting today lecture 2 on cryptography with Python. So I'm going to first give you some introduction to cryptography, and we will quickly switch to how we can use Python to play around with some basic schemes in cryptography. So one of the basic things you will find everywhere in information security is cryptography. Okay, so cryptography is just one of the important science where we learn about how to ensure that two parties or multiple parties are able to communicate securely without any possible breach. Okay, so the concept goes into the fact that if I am a party A, usually we use Alice and Bob. So if I am Bob and I'm communicating with Alice, then the message I am sending as Bob to Alice should be encoded. Usually they use that word, or encrypted. Okay, then when I transfer my encrypted message over the channel of communication to Alice, then the concept is that when Alice receives the message, Alice is going to receive an encrypted message, but Alice should be able to unravel the message and then see the content. Okay, so for this to be possible, then there should be some mechanism that will facilitate such a encryption and decryption flow. You see something called plain text, and you see what we call the ciphertext. Okay, so if you have two users, let's say Bob okay, and then you have Alice here. Let me just use A for Alice. Now Alice and Bob would want to communicate, and this is over a communication channel. Okay, so a communication channel, think about it like an internet. Okay, so Bob has his device here, and then Alice has this device at another end. Now there is going to be a transmission of data between Bob and then Alice. Now, how can they ensure that the data that is going to be transferred over this communication channel is transferred successfully without any attacker getting access to the information? Okay, all right, so usually we call the attacker as Carol, or the adversary is another word we use for it. So the adversary is assumed to be somewhere here in the middle of the communication channel, and then he has an intent of either monitoring whatever conversation that is going on between Bob and Alice, or he wants to tamper with the content of the message. Okay, so that's the intent of the adversary. Okay, now this channel of communication is open. The internet is open. The internet is just open. Anybody can do whatever they want on the internet, right? So it's not a secure channel. So you're having Bob and Alice communicating. Now, to make this possible, there needs to be a use of a mathematical function. Okay, so the bedrock of almost all security things we are seeing is mathematics, and the bedrock of cryptography is mathematics. So you have to use a certain mathematical function to ensure that this happens. So with your plain text, let's say plain text is P, then you get an encryption function. Okay, so the function that is going to enable you to get the plain text encoded is going to be the encryption function. So you're going to have E. Okay, I'm just trying to get this script here, and then you're going to have P. Oops. Okay, so into bracket. Okay, this is how we represent a function. Is that not so? So E of P now is going to be equal to some ciphertext CT. Okay, CT. Right, so that's how the process is going to be. Now, if you want to get the ciphertext back into the plain text, then you have to also have a function that takes it back. Okay, so the function now becomes D of what? D of what? CT, exactly. So D of CT. All right, and then that will be equal to what? that will be equal to plain text, right? Which is what? The P. Okay, so E of P gives us CT, D of CT gives us P. Okay, now there is something that is obviously missing in the process, because this encryption function cannot just work without a parameter that is so important. Okay, and that parameter is the key. Okay, so I should have even asked the question like, how is the reverse going to be possible? How is E of P going to be equal to CT and D of CT going to be equal to P? We need to have a key. Okay, so is the key, so usually we indicate the key as a subscript right here, so that E of P is working along with a key, and then that key converts the P into a CT, and then when you are getting it back again, you need a key. So it's actually usually a subscript, but I'm going to write it here for want of space. Okay, so one thing that you quickly notice right here is that the key that is being used is just a single key. Is that not so? So whenever there is a single key in the process of encryption and decryption, then we call that encryption mechanism as a symmetric encryption. Okay, right. So take note of that. So quickly the question comes as, when you are doing symmetric encryption, then you need just a key. And then that key often is called a shared key, sometimes also called a session key. Okay, people have different names of calling that, but it's a single key in the process. That is called symmetric encryption. Okay, now the advent of symmetric encryption ensured that two people are able to communicate over a channel, or if you like, an insecure channel, ensuring that they are able to receive messages safely. Now, when you encrypt a plain text, what you are able to achieve is what we call confidentiality. So confidentiality is achieved with the mechanism of encryption. Okay, and the concept of confidentiality is simple. What does it mean? Confidential. If we said something is confidential, what does it mean? It means nobody is able to see the content. Is that not so? Or nobody is able to, if you like, open it. Okay, so confidentiality enables us to ensure that no attacker or adversary is able to read our message or have access to our message, that we are sending over the insecure channel. Is that okay? Okay. So going down again, you would realize that this term confidentiality is part of some three common terms as far as cybersecurity is concerned, and that's what we call the CIA triad. Okay, so that is the confidentiality, and then the second word is integrity, and then the third word is availability. Okay, so these are three common terms that fundamentally you should know in cybersecurity. But to achieve confidentiality, you use the mechanism called encryption. Okay. Now, the second aspect is, which comes quickly as a question, is that, okay, you are able to ensure that the message that is being sent across from Bob to Alice is confidential. So it means that if the attacker has access to this encrypted file, the attacker is unable to see the content of the file. Okay, so fine, you have achieved that. However, you are not denying the fact that the attacker could have access to the encrypted message. Okay, so if the attacker can have access to the encrypted message, then what next? Can't the attacker decide to, if you like, append some text or some string or some function to the encrypted message so that the other person who is on the receiving end is unable to decrypt? Is that not possible? Okay, so the attacker can also do that. So how do you ensure that if even the attacker has access to the encrypted message and he has appended a string or a function, you are able to determine that the attacker did that? Okay, hence you can either request for a new ciphertext or, if you like, try to decrypt. Okay, yes, anybody with an answer, an idea? So yes, that's where the concept of integrity comes into play. So integrity is basically about, I want to be sure that this message that is being sent across has not been tampered with. Is that okay? Okay, so integrity enables you to, you know, that property of integrity is to assure that nobody has tampered actually with the data that is being sent across, if you like, the encrypted data that is being sent across. Okay, so how do you achieve integrity? What's the mechanism for achieving integrity? Yes, anybody here? Now I've told you. Yes, yeah.
Probably it might not be only one medium that this information can be shared, but both can share with others. If the first one is sent through one medium, then you think like maybe if this the message received is tampered with, probably you can find out another way of receiving it to compare whether the original message, the message received is the same as the original message. If it's the same, then it's accepted. Or if it's not the same, then probably you can suspect some foul play elsewhere.
So one of the ways to ensure integrity, okay, making sure that there is trustworthiness with respect to that data that is being received, or you are maintaining what exactly is the content of that particular message and that it cannot be tampered with, is to use hashing. All right? So that's the mechanism. So you use hashing. Hashing is the mechanism to achieve integrity. Okay? And sometimes, depending on how you constructed a signature can also enable you to achieve integrity. Then you see quickly that if you want to achieve confidentiality, you need encryption. If you want to achieve integrity, you need hashing, right? Okay. And then availability is the concept of making sure that whatever you are encrypting, whatever you are sending over, is able to get to the receiver, and then the receiver is able to access it without any challenges. Okay, so that is it. Now, beyond this CIA triad is the concept of authentication. Authentication that enables us to achieve one property again called non-repudiation. Okay, so non-repudiation. So the mechanism to achieve, I'll talk about it. The mechanism to achieve non-repudiation is authentication. Okay? So if you implement an authentication mechanism, then you are able to achieve non-repudiation. So what at all is non-repudiation? So the concept of non-repudiation arises quickly when you are still looking at this same diagram here. So first off, we are saying, okay, you have been able to send the message confidentially to the other receiver. You have been able to ensure that there is integrity. But there could be the point where the person who sent the message to you would want to say, hey, I never sent the message. So how are you able to check and see whether the sender of the message is actually that person? And he cannot deny that he is actually the person who sent the message. Okay, so that question also comes in, how do you ensure that the sender is unable to deny the fact that he actually sent it? Okay, so now how to achieve that, you use authentication. Okay, so in some sense, authentication can help you to achieve integrity, and authentication can help you to also achieve non-repudiation. Do you understand? Okay. Now, what is non-repudiation? It's big English, is that not so? So that's the concept of ensuring that the sender cannot deny that he sent the message. That's all. Okay, non-repudiation. All right. So some of the mechanisms in authentication is like digital signature, right? So digital signature. Digital signatures ensure that Marcy sent me a message. Marcy cannot deny that he sent me the message because it's Marcy's signature that is on it. Okay, that kind of thing. Right, you wanted to ask a question? You're fine. Okay. So these are very important basics in information security that you have to know. Now, I'll add another one. So if only you knew about confidentiality, integrity, now you know about what? Non-repudiation. Is that not so? Okay. And we said non-repudiation, the mechanism is authentication mechanism. And there are a lot of examples of authentication mechanisms like digital signatures and so on, right? Okay, now what if the sender of the message would really want to be able to deny that he didn't send the message? How can we ensure that the sender of the message legally or legitimately denies the message that he's sending? Because there might be exemplary applications where somebody must necessarily be able to deny. Do you know such applications? Do you know such applications? Okay, I'll give you an example. So in the system of election, if we were all in one organization and we were doing an election to elect the chief executive officer, or maybe let's say we want to elect the guy who will be the head of the IT section. Okay. So there were two people who were eligible for this position, and we all in the IT directorate are supposed to be voting for one of them to become the next IT director. Is that not so? Now, I want to be able to vote without coercion. I want to be able to vote without what? Coercion. In other words, if that guy turns out to be the next IT head and he has access to everything, then he can at a point look at those who voted for him. Is that not so? And then say, man, say, oh, okay, so me and you day here now, you be that guy. You are not in my team, right? So the point is, you should be able to develop a mechanism that allows Mase to be able to vote without any coercion, with free mind. And that is where you should be able to enable Mase to vote so that at the end of the day, if the head goes to check those who voted, Mase can actually deny that he's not the one who voted for the other person. So this is an application. How do you ensure that this happens? It's called the concept of deniability. Okay. The thing is, what is the mechanism to achieve deniability? So there is a whole direction called deniable encryption. Okay. So you're going to actually encrypt, but you are encrypting in a deniable way, so that at the end of the day, you're able to prove with probability that the receiver can also construct the same encryption mechanism. Hence, it is impossible for you to prove that the sender actually sent the message. So that's it. So we have this direction of deniable encryption. We have the direction of deniable authenticated encryption. We have the direction of deniable authentication. So now, we've been able to explain confidentiality, we've been able to explain integrity, we've been able to explain availability, we've been able to explain non-repudiation, we've been able to explain deniability. And we all know the mechanisms behind them. Is that fine? So now let's move on to see how we can write codes for them. So we're going to start with basic codes, right? For some basic mechanisms. And then we graduate gradually into some form. Okay. Right. Any questions till now? So I don't think I have to explain these terms again because I've talked about them. And characteristics of modern cryptography is pretty simple. Okay, so it operates on bit sequences. In other words, every message that you have is rendered as bits, right, or as zeros and ones, so that the computations can be performed on them. Okay, right. So cryptography uses mathematical algorithms for securing the information or whatever message you are sending across. You get to have Bob here and Alice here, and they want to communicate over the channel. Then there is a message. So let's just say that the message is this one. Now, let's see. A has got his public key somewhere. Now, listen guys, the word public key obviously means that the key is not private, it's public. Is that not so? So public key is public and is outside somewhere, maybe on the internet. So Bob can just quickly pick the public key of Alice, so that's PKA, okay? And this PKA is obviously some characters, all right, that was generated from a mathematical function. Okay, so this mathematical function that enabled you to generate this pKa has a connection with another key we call the secret key or the private key. Okay, so the private key and the public key has some mathematical connection. Are you getting the point? So there is this mathematical function that you have to use to create your public key, and then out of that you also get your private key. However, you put the public key outside. Okay, so that anytime someone uses your public key to encrypt a message, because you have that private key, you are able to decrypt. And because there exists some fundamental relation between them. Do you get that? Okay, so that's it. So Marcel would just do that. So yeah, so then the key to encrypt this, maybe just the key like this. The key to encrypt this will be the pKa. Okay, now once this is done, you would notice that the B, Bob, is not actually using any key here. That is of his own, right? He's just using the key of the receiver. And then the file will go here all through the channel, and it's an encrypted one. Okay, let's do this zigzag to show that. So once this zigzag file comes here, what will Alice do? Yes, guys? Yes? Alice will take the private key, and often in information security we represent that by SKA. Okay? So that means SKA of the Alice, right? So then Alice would use her key to just decrypt, and then would have the plain text. This is one interesting thing about information security, okay? Whenever an algorithm is developed, the algorithm is public. It's there. Everybody knows how the algorithm works. And everybody understands the mathematical foundations that went into that. So, if this algorithm is being used in developing certain tools that enable secure communication, then we are able to determine whether that algorithm is solvable, or if you like, whether the hard problem that was used in the algorithm is solvable. If it is solvable, then it inherently means that the particular tool that it was used for is also vulnerable. Do you guys get what I mean? Now, let me break it down with an example. So, we are talking about public key cryptography. There are just multiple examples of that. You might have heard of RSA. RSA is a public key cryptography technique. Okay, I mentioned attribute-based encryption is also a public key cryptography technique. Okay, and so on. Now, all of these techniques are based on some hard problems. Hard problems. When I say hard problems, I mean problems that have never been solved in this world. Mathematical problems that have not been solved in this world. Okay? So, in mathematics, we call them intractable problems. They have never been solved. No one has ever been able to solve it, even with some powerful computers that we have currently on the earth. So those are the mathematical problems that are used to construct the schemes. And when the schemes are constructed, the constructor of the scheme have to prove that because this particular mathematical problem has not been solved by anyone else, then our scheme is secure. And then if our scheme is secured and it is now deployed into certain tools, for instance, maybe the ATM machine or your RFID card to the hotel, or maybe even in WhatsApp or any of these tools that you're using, then WhatsApp can say, yeah, we are ensuring end-to-end encryption. Why? Because WhatsApp is aware of the scheme or the mechanism that was used, okay, in creating their tool. And they know that that mechanism is based on some intractable problem. So if they say that it cannot be hacked or it cannot be broken, they are saying that on the basis of the difficulty in the hard problem. So the point is that if anybody could solve that hard problem, then they cannot brag again. Just type RSA numbers. And then you get to Wikipedia. And then you can see for yourself RSA numbers that have been broken. For instance, RSA 100 has been broken. So this is, you are having 100 decimal digits, okay? And then you've been asked to find the two numbers that were used in generating that 100 decimal digit, okay? Because those two numbers one ends up being in the private key, okay? Yeah. So if you're able to determine that, then you're able to know the private key. Okay, so your question about like how to know the private key stems from here. So you see that in the algorithm for RSA, everybody knows the algorithm for RSA. It's not a secret. Everybody knows it. And everybody knows how the private key is generated. Everybody knows how the public key is generated. It all stems from the prime numbers. And it uses concepts of modular operation and all that. So these are fundamental mathematics that people understand, right? So once you're able to find that, then that's fantastic. Then you go. Okay, so the people who found that said these are the two numbers that was used in the RSA 100. So it's a dead news now. Okay. And they used, of course, some kind of computer, a parallel computer, to do that. Okay, so you can calm down. Like most of them have been broken. So yeah. So currently RSA 2048 is what is being used. But we want to see the SSL service that they are using, and what kind of cryptographic mechanism that the SSL service is using. So you come to connection is secure, and then you come to certificate. And then you come here, you're looking at the certificate. So they are getting it from DigiSet, okay? So DigiSet is a company that provides SSL, right? Okay. And then they are using RSA SHA-256, okay? So you know about RSA now, right? You know about RSA now, guys? Okay. And then you know about SHA. SHA is what? It's a hash function, right? So who can now tell me? So now they are using the SHA to achieve what? We just talked about that. Integrity. Is that also? Okay. And then RSA will achieve what? Okay. So it means that when there is a TLS on the server, okay, communication, when there is TLS, then communication over the network is encrypted. Is that also? Okay. So when there is none, it means communication is not what? It's not encrypted. Is that also? So from the client to the server, any message that is being transmitted is open. So if an attacker intercepts a packet or intercepts anything, they're able to understand and read what is going there. The public key algorithm is what? Is RSA. Is that not so? But this is actually RSA 2048. Okay? It's not the RSAs that have been broken. It's a very funny idea. This is about trying to encrypt and encrypt again. Okay? So people think when they do that, the capsule created will be efficiently secured, you know, but I think that most important thing is to ensure that your encryption algorithm is based on a very good hard problem. Okay, then that's fine. You don't have to just do a double one. Makes no sense, actually. But people do it all right. There is also the concept of hybrid cryptography. So if you do not want to use symmetric or public key, you can also combine them. You can combine hybrid, you can combine symmetric and then public key, all right? So that's the concept of hybrid cryptography. And we have what we call the key encapsulation and data encapsulation. Okay, these are mechanisms in a hybrid crypto system. Okay, so maybe later you can read more about it. Here I indicate how an encryption can be done with hybrid cryptography system and how to decrypt with a hybrid cryptography system. So now to trying to program some of them in Python. So what we are going to do is we take the first example and maybe the next class we will continue. So we will start from symmetric schemes. Okay, so symmetric schemes, and we will start with the traditional symmetric algorithms. Okay, very, very basic. And then again, people will not even use it. Okay, so we call them school book examples. Nobody will use these ones. Okay, but before that, you have to install cryptography, the cryptography module, and you're going to use pip to install that. So the first algorithm we'll look at will be reverse cipher. Okay, and reverse cipher is simply reversing the text. Okay, so you have hello, and then hello can be reversed to OLLEH. Nobody actually uses this because it's even easy to guess. The problem that it is based on is very easy to solve. What is the problem? The reversing problem. Is that also? So if you reverse, you can reverse, and you get the original text. Is that also? So it's very, very easy. Okay. So this is the code for the reverse, and we can do it together. PyCharm, and then let me go to view. Just create a new file. You know how to do that already. We talked about that in the other class. Okay, so it's very simple. First, we need to take a message. Okay, so we say message. And then again, I said that you should install cryptography. Okay, so you can do pip install cryptography. But there is a simple way to do that. Okay, if you're doing this on your terminal, you should have connection to the internet. Okay, so on the terminal, you can do pip install cryptography. Okay, that's fine. Or you can just do everything right here on your in your PyCharm. You can just go to File, you go to Settings, and then you go to your project. So you go to Python Interpreter, and here I have these packages installed. You see pip, setup tools, wheel, and all that. So you do plus, and then you search for cryptography. Okay, so you see cryptography right here, and then you say install package. Okay, so then you get it installed. Or you can come to the command window. Okay, and then you do pip install cryptography. Okay, but because I have it installed already, it will tell me that blah 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 blah. So requirement already satisfied, okay, because I have it already installed, right? But if you do pip install cryptography, then you should be able to get it. That's fine. Okay, so now let's get back to this side where we are going to actually try to do the first simple code. Okay, so this is what we are doing. We said let me just zoom this a bit. Okay, you are all able to see this, right? So message, I'm starting with message, or if you like, plain text. All right, so maybe I'll just start with plain text. So plain text is equal to, then let's use a string, but sometimes you could also read a file in, right? You can open a file and read it in, that's also fine. But let's just begin with a string, and then I'll just say, this is my first text, okay? Now I go to the next line, and I want to reverse, okay? So how do I make sure that the reverse happens? So first I'm going to declare a variable, and then allow that reverse text to be stored in that variable, okay? So I'm just going to say cipher text, okay, is equal to quote quote, because that's going to be what is going to be holding my ciphertext. Okay, so then the next thing is that I want to now find the length, okay, of the text, of the plain text, of the characters in the plain text. Okay, store it in a variable, and then now use a condition, okay, a looping condition to do the reversing. Okay, so that's basically what I'm going to do. Okay, so the reason is I want to be able to reverse each character. All right, so I need to be able to deal with each element in the string, okay, or each character in the string. Okay, so I am going to treat it as a list. Okay, right, so that's it. Now what you do right now, how do you find the length of any anything, any any string or whatever? So it's len, right? Or any variable. So I is equal to len, and then what you do is that you put the plain text here, okay? Because that's, you're trying to find the length of it. And then you're saying -1. Okay. So then you're saying while I is greater than or equal to 0, okay? While I is greater than or equal to 0, then I want my ciphertext to be equal to the ciphertext plus the message with respect to a particular text or character in it. Now we're going to be treating it as a list. Okay, so you'll be seeing the indexing box right there. Okay, so here we go. So I say that ciphertext should now be equal to, okay, so ciphertext plus plain text. But then it's going to be treated as a list with where I will be forming each character in the string. Okay? Okay, so. All right. So now once we do this, we say then I is equal to I minus 1 for our looping to happen. Okay. So are we good? Now we may get an error here because we have to bring a full color. Okay. So now once we are done, this will essentially help us to do the reversing. Okay? And these are warnings for spaces. That's fine. Okay, so I mean, nothing will happen if you leave it like that. There's nothing wrong. So now I make my print statement. So I'm saying should print what? It is going to print the ciphertext. Is that okay, guys? So you say print the ciphertext the ciphertext is, then I want to, is ciphertext, right? Okay, so this should work fine for us. Okay, so this is going to do the reverse. Okay, so you can imagine if you wanted to do any symmetric encryption, or if you like, this is a traditional one, right? So just playing around it, you just do this reverse thing, you send it to someone, then they are able to decrypt it, and then they know what you actually want. Is that not so? Okay, so we will also program the decryption part. So this part is only going to encrypt it. Okay, so how do we decrypt? Do you understand? Okay, so to decrypt, then we are saying that when we decrypt, okay, so plain text coming into a ciphertext. So when we decrypt, we want to call that, obviously should be called a plain text, all right, but let's use the word decrypt. Okay, so decrypt is equal to ciphertext. Okay, so now do you guys follow? You understand that? So decrypt goes ciphertext. Then we are saying that plain text O standing for maybe the original plain text, right? So plain text O it should be stored here. Then we will follow through the same process because it's reversing, so we have to just reverse it. Is that not so? Because when you so the idea is that when you reverse the ciphertext, you get the plain text again. Is that not so? So what we are just doing is to reverse the ciphertext. So we go through the same reversal process. Okay, so it's pretty easy. So plain text O standing in for that one. Then you can do maybe let's, for purpose of clarification, let's use J is equal to length of what? Decrypt. Is that not so, guys? Are you guys with me? Minus 1. Okay, so then you do your while J is greater than or equal to 0. 0 full colon. Then here you are with the plain text O. Okay, plain text O is equal to plain text O. Is that not so? Okay. Then now we have to treat it as a list, right? We treat decrypt as a list. Okay, so decrypt as a list with J. Okay, then we do J is equal to J minus 1. Then we can print our the original plain text, okay, is, then we give a comma, then we give, what are we printing now, guys? Yeah. We are printing plain text. Plain text, so that's what we are printing. Okay, so let's see how it goes. Let's review again. So what we are doing here is that we have a plain text that is a string, is just a string. This is my first text, and then we want to store the reverse of that in the ciphertext variable, and then we are saying that to do that we need to run a loop where we are treating the string as a list, and then we refer to each of the elements in the list at a time and do the reverse. Okay, so that is the looping we have here, and then we at the end of the day print this particular variable ciphertext, which is going to be holding every element, okay, at the end of the day. Right, so to decrypt, then we are saying that we just need to reverse the ciphertext. Okay, so here decrypt is equal to ciphertext. Here we are referring to this ciphertext, and then plaintext O stands for your plaintext, original plaintext. Okay, so we are going to store the original plaintext in this variable, and then we again going through the process of reversing. Okay, so we treat the ciphertext as a list, and then now we use J to point to each of the elements and then try to reverse, and at the end of the day we should have our answer. Okay, so let's run and see how this goes. Any question, guys?
Why are you taking
One? No, you are treating it as a list, right? So, and then for I, when I declares the length, it is declaring it as a digit. Okay, If you do learn plain text, it's actually literally going to count each of the text and each of the characters and give you the number. Okay, so if you do learn hello, how many characters there? HELLO is not 5. So it's actually going to print as it is going to look at it like 5. So it's going to be 5 minus 1. So 5 minus 1, you get 4. Is that also? Then it takes you, as a list, it takes you to the 4th element. You understand? So it goes like that. Okay, good. All right, so we don't have any errors showing, just some warnings, maybe probably for spacing. Let's run. So yes, our code is working here. We see the ciphertext is what? The ciphertext turned into this. It's a reverse of it, right? So this is the ciphertext that we're probably going to be sending to whoever in this symmetric process, all right? But then to get the original plain text, we get it back. Is that also? So the original plain text is, this is my first text. Is that also? And then the ciphertext is this. So that is a demonstration of how to use reverse, how to use Python to code reverse cipher. Okay? This is a very basic one. So if you wanted to do this in a very fun way, then you can ask a user to make an input. Is that also? So now you get to that level where you are playing around with it. So you have to receive an input. Okay, I'll let you see. Okay, so you can ask the user to input any character, and when they did the input, then your loop gets it reversed, and then it encrypts it. Is that also? And then at a point, you can get it decrypted as well. Do you guys get that? So I'm giving that to you as your homework. Now let your program accept an input from a user. So the user should be able to enter any string of characters they want, and after they have entered, then your program does the encryption, and then at the end of the day, you should also allow the user to enter the ciphertext, any ciphertext, and your program should be able to decrypt and give you the plain text. Okay? So you can, if you are very happy about this, you can take it to the object-oriented level, okay? Where you just take this logic and then you build yourself a simple encryption and decryption tool. Okay, so and then the mechanism on this is just reverse cipher. Are you guys following? So if anybody will build a tool and put it in the market, then it's going to be based on some mechanism, right? So if, for instance, I built my encryption and decryption tool and I hosted it on some server, and you said you needed an encryption tool and you went to download that, and you have no idea what mechanism that is behind it. Is that so? Yeah, you don't know if I use reverse cipher, right? So you just click, 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 and it's all working for you, but you have no idea what mechanism is behind it. Now, if I do an investigation and I find out at the end of the day you use reverse cipher, then it's very easy, right, for me to be able to determine what's the answer. But actually, in practice, nobody uses reverse cipher. It's just a very old one, I think. Nobody. Yes, you have a question? I think the time is up. Next week we will continue writing more complex codes for other algorithms.